Hey guys, welcome back to not bioinformatics, I'm sorry, data products with R. In this video we're going to be doing heat maps, and so heat map is a way to visualize intensity, right? And so we have, the data set we're going to be using is the lung cancer death. It's a data set from the UK. Every month number of lung cancer deaths is measured. On one axis we have the year, on the other axis we have the month, and then our actual data within the heat map is going to be the number of deaths. It'll make more sense when we get into it. So without further ado, let's go ahead and get started. Alright, first things first, let's open up R and a new R Markdown file. We'll call this one Heat Maps. Let's get rid of this jazz. Alright, so just annotate. Let's get started with heat maps. So first things first, if you don't have it installed, install packages Heatmap 3. I already have it installed, so I'm going to just load it. Library Heatmap 3. And run this real quick. Alright, now let's get our data. So our data, we're going to do data is LDeaths, and then we have to do some transformation because the thing with the heat map package is it requires your data be inputted in a matrix. So if I just run down here in the terminal LDeaths, you see we get this nice matrix-like thing, but if we actually run it and save it as an actual data frame or matrix or, oh my gosh. Okay, so if I run this code, let me get rid of this part. Alright, let's try saving LDeaths. So you can see we have it as a time series data set up here, and if we try to do heat map stuff, it won't like that at all. So we have to transform it. So we're going to create another one called data2 and do call cbind split data cycle data. So now if we run this, you see that we have data2, and this we have now as an actual data frame, or what looks like a data frame or matrix, but we've lost our labels. So now we need to do dim names data2, and then dim names dot preformat dot ts data. So now if we run this, you should see we actually got our years back and we got our months back, which is perfect. So everything's where we want it to be now. Now let's generate a heat map. Okay, so heat map, we'll just call data2. Let's run this. Just a basic command. And so this is just a general heat map, and what it automatically does, the defaults, is you can see it clusters like values, right? So we've lost our sequence of months. So January, February, December, March, April, November, October. So we've lost that, and we've lost our years. And so what it's doing is it's trying to put like values together. And as you can see, we have all the dark red generally together, and then all the yellow generally together. So what this is saying is that, okay, these months, and we have our dendrogram too. So these months over here have more in common than the rest of the months, and these months over here have more in common than the other months. And so if I were looking at this, and this has no biological basis, I'm just guessing based on the data. But this is lung cancer deaths, right? And so the coldest months, so the months you're most likely to get pneumonia or the flu or something like that, those have the most deaths. And so that could be some sort of comorbidity with lung cancer, I'm guessing, right? Because January, February, December, and March, arguably the more colder months. November, October, and April could also be in there. But then you look at the three warmest months, June, July, and August, and September, those are the lowest deaths. I have no I don't know the study that well. There's no biological relevance to it. I'm just guessing, but that's kind of what the graph shows me, right? Is that colder months have more lung cancer deaths than warmer months. Interesting. Okay, so let's keep going. Heat map, data 2, rho V equals NA, cal V equals NA. Okay, so let's run this one, and I believe now you see that we have our order restored. So if you compare the two, there's no dendrogram to show us clustering, right? We have natural clustering, although December, the cold months kind of span, across here. But you can kind of see this better from the calendar perspective, where I was making my guess about, cold months and pneumonia and things like that. But January, February, March, April, cold months. As it gets warmer, May, June, July, August, the number of deaths go down. So interesting. And this is one of the big things about data visualization, is being able to tell a story, presenting your data in a way that a consumer of your data is able to look at it and be like, that makes sense, right? And so without even reading the study, just looking at this data, I'm making a conclusion, but the authors should be presenting this data in a way, not that they neglected to, it's just because this is thrown into R as a play data set. But the whole point is to convey a message. And the message I'm getting just from playing with this data is that cold months, there are more deaths in the UK during these years from lung cancer than in the warm months. So it's cool that you can kind of like tell a story just by a visualization, right? Okay, now let's play with the colors. So let's do RC equals rainbow, not rainbow, rainbow, and row data 2, start equals 0, end equals 0.3, and let's do CC, rainbow, and row, or and cal, data 2, start equals 0, end equals 0.3. Okay, so what we're just doing with those is we're just setting a palette using this rainbow function. Rainbox, rainbow. And so we'll be able to apply it here now, right? So if we go to, now let's apply our color selections. So you can play with those numbers, the start and the end, and it will change your palette. So let's do heat map, data 2, and then we'll say cal side colors equals our stored value, which was CC. Okay, so you can see that I've added a coloration to the columns here based on how closely together they're related. So it doesn't make a lot of sense for this data set to do, but if you're doing gene expression data, so if you look at a lot of differential gene expression, you'll see a lot of heat maps, and they'll cluster genes together based on if they are turned up or turned down together based on your experiment, right? So in my example, I do work with gravity research on the space station, so we'll send plants up into space and we'll keep plants down on the ground, and then we'll look at what genes are differentially expressed. And so based on the 20-some thousand genes in the plant that I use, Arabidopsis, we can do this clustering to see which genes are always turned up in space and which genes are always turned down in space, and do this heat map, or genes that never change, right? So there's more utility to it than this heat map or this lung cancer data set, but this is good to play with. Okay, I am getting distracted. So now let's do library. So this is, so again, you can use the install packages if you don't have it. Color, brewer. So this is the cool stuff with ggplot and some of these other packages like Heatmap. There's a lot of customization. So color, or col side colors equals cc, and then we're going to do col equals color ramp palette, brewer dot pal. I'm going to say 8, which is the number of colors, and then p lowercase I yg, which I think is pink, yellow, and green, just to be funky. And then 25, I think, is like the scale of colors, like the number of colors in our scale. You'll see what it means in a second. Okay, so pink, yellow, green. We've just changed it to the point where instead of being an actual heat map, meaning warm and cold, well, we have pink and green instead, which is, I don't know why I picked pink and green. Very Eastery. Okay. Okay. There's more that we can customize. So if you wanted, like, if you were doing this for a, poster presentation at your school or something, you could pick your school colors, or if you're doing it something with, like, say you were doing, alive plants and dead plants or something like that, you could pick green and brown or something of that nature to kind of, tell your story a little more. Col side colors equals cc, scale equals column. Let's run this code. Col side colors. Data 2, col side colors equals cc, not comma cc. All right. That's just the same thing that we did right here. Okay. Just take that right out of there. I don't know why I repeated that code. All right, last thing. Library, gplots. Not ggplot, just gplots. So you might have to install it. Heatmap.2 instead of heatmap3 that we used before. Data 2, col side colors, and you could do row side colors too if you wanted to. Equals cc, col equals color ramp palette. Oh, this is the same thing too. You know what? Oh no, this is a different heat map, sorry. Brewer.pal 8. We'll do the same colors. PIYG. Oh, I remember what this is. Capital P, I, capital Y, capital G. And then 25. Alright, let's run this instead. Brewer.pal 8. Nope, comma. 8, comma, PIYG. Still wrong. Color ramp. Only one L in palette, isn't there? There we go. Okay, so this gives us a histogram on the column. So it's kind of hard to see here because it's kind of tiny. Can I break it out? Well, that's way too big. Let's see if I can drag this down. Okay, so you can see here we have a histogram based on each column. So you can see that like the most total deaths in this were Oh, see, it doesn't really work very well for this. Oh, so it's saying, okay, what's the count of the amount of deaths, right? So we had 1 month where we had very, very low deaths rate, and that was February of 1976. We had 10 months where we had this color. Can you see my mouse? Kinda. Where we had this color, which is the third color down. So it's probably these colors. It's kind of hard with a color map sometimes to like map these things, right? But you see that like the most common, most common was the highest death number, which is probably like 2,000, right around the 2000s. Was the second most highest, second highest, and then you know, this is a not normal distribution. Anyway, so this is, you know, you can add layers to it. This isn't a great example, but you can add a histogram to kind of show what your most common color on the color map is. I wanted to show you the option. You can add more to these maps than what is, you know, what I've shown today. And so the histogram, you might never use it, probably will never use it, but it's out there. There's other things too that you can do, and I don't want to get like too far into the weeds, because heat maps, you know, heat maps they're kind of an eye catcher because of all the colors. You know, we're naturally attracted to all these colors, but the utility sometimes leaves a lot to be desired. I know that when I read manuscripts with differential gene expression, it's sometimes just too much information. You know, you look at 20,000 genes in multiple different like reps and things like that, and you get these, you can see clustering, so you're like, oh, there are clusters of genes that are, you know, going up and down together, whether between these two conditions. But can you pick those out? Like, I can't look at a color map and then be like, oh, that gene is a heat shock protein, or that gene is hexakinase, or whatever, because there's just too many. So you get the picture. Like, this goes to the whole, you know, point of the course is making your data tell a story and creating a product that is digestible by people. And so heat maps, it depends what you're going for, that wow factor, but it might not be the best way to tell your story. If my story in the example today was cold months lead to more deaths in lung cancer people, that story can be easily told because I just made that story up and it seems to fit the narrative or match the picture. If you have a much more complex story, heat maps might not be the best thing. But that's how you do heat maps after I just, you know, crapped all over them. So anyways, thanks for watching this video. I hope you learned something. I hope you enjoyed. If you haven't subscribed, hit subscribe. And we'll be doing more visualization. We'll be doing more preliminary data analysis. So stick with me, check out another video, and I'll catch you in the next one.